my slides?
Yes, yes.
Okay, thank you very much. And the first report, my report, is about synthesizing optimal signal processing algorithms in cognitive synthetic aperture radars. And I will start from the application of synthetic aperture radars and this technology. We have a wide application of SAR system is the short name, and these SAR systems are installed almost on every these days almost on every remote sensing satellites for Earth investigation, but really they can be applied also for military application. And some application, it's topography, oceanography, deforestation monitoring, movement tracking, earthquake monitoring, and others. And exactly spaceborne synthetic aperture radars gives possibility to achieve high resolution capability, weather independence because of radio waves utilizing day-night imaging capability due to own illumination of the signals. It's active radar. Complementary to optical systems in the question of resolution. For example, Ukraine, thanks to Ukrainian people, we have bought the satellite that is called ISI from Finland company, and it has resolution 25 centimeters, and it complementary to modern optical systems. Polarization signature can be exploited, and we can understand physical structure, dielectric constant, and other parameters. And in numerous applications area, as we saw before at the previous slide. And exactly synthetic aperture, this creation of artificial antenna on the board, it's some algorithm, it's some technology that was developed almost 50 years ago, and it's used for moving, for aircraft, for spacecraft, for moving objects. It can be used to improve resolution of radar images. And here you can see the concept. The concept is in the following. We can see using the onboard antenna. It's usually small, and it has like wide angle of view. And while we fly and pass some point here on the surface, we can see, because of this wide angle of view, we can see this object a long time. And using coherent radars that receive signals according to this information of phase, we can collect these signals. It's shown here. We can collect these signals during time of flight, and then all of this information can be processed in time. And this processing of so-called trajectory signal give us the higher resolution. It comes such situation as we receive signal by big antenna array, and processing signal from this big antenna array gives us high resolution and give us like maybe it can be achieved like 100 times narrower antenna pattern, and this antenna pattern already has good resolution on the surface. This is the idea, this is the concept. So the coherence of the radar, the wide angle of view, and it must be moving platform. And the concept of cognitive radar. Today we can start from the concept of cognitive systems that was introduced by Professor Simon Hyken in his work that is called Cognitive Radar, A Way of the Future, in 2006. And he told that any dynamic system can be called as cognitive when it has some basic human condition: the perception action cycle, the memory, the attention, and the intelligence. And he shows the very nice example of spectrogram of sonar signals from 4 different types of bats while they're hunting on some on some objects. And while they are hunting, they sound signal in acoustic region. And this signal can be detected, and we can see that we have two scales, it's two coordinates. It's like time and frequency. And where they are searching the object, while they are just searching the object, they use short pulses in time and relatively wide, some of them. It's 4 types of bands and relatively wide frequency range to increase the amount of information, but like small portion of energy. And this portion of energy, they are like have long period of time between repetition, so it has a long repetition period. But when they find the target, they start the approach process, and they increase the period of sounding the signals. And also some of them change frequency characteristic of the signal. And while they catch the target, they increase this period of signals transmission to like maybe 5 times or 10 times more rapid transmitting the signal. And also you see, for example, this bed, it has very wide frequency range. So all of this dynamically change, and this is the example how the cognitive radar has to operate. While because of changing environment conditions, the radar has to change its own parameters and has to teach and has to uh, have memory and intelligence. So this is idea, the general one. And in 2010, Joseph Guerci, he represented the book Cognitive Radar, a knowledge-aided full adaptive approach. And he determined the structure of cognitive radar. And this structure has to have adaptive transmitter, adaptive receiver, adaptive antenna array, or maybe any other antennas that can change antenna pattern characteristics. Then dynamic base that can change during the time, also base of the previous measurements. Radar schedule, it can be removed, and radar can change its parameter automatically, or it can be radar scheduler, and it defines the changing of all of the parameters. Key knowledge aided processor. 1, 2, 3, 4, 5, 6 components of cognitive radar should be cognitive radar should have. It's for sure and for all cognitive radars, they should have such structures. And we came to existed results. We studied the already existed devices and existed theories of this cognitive radar. We didn't find a lot of information between Ukrainian scientists, and maybe we did not clearly understand the international scientists. But we found that we have some systems that just constructed according to this this structure. They use separately adaptive receiver, separately adaptive transmitter, separately this knowledge aided processor, and create by themselves create the algorithm of all of this structure operation. And for example, we can see here block diagram for some cognitive radar prototypes. That change central frequency because of high level of noise or high level of background radiation, or maybe change frequencies because of some jamming. And they just used this structure and created their own device according to this structure. And we found also there are some examples of creation such systems for detecting different aircrafts and measuring their parameters, and create some classification of these radars, of these aircrafts, and also in space changing the amount of energy in space, changing antenna pattern characteristics because of different characteristic of the surface. So such a very adaptive system that can change its parameters not only to receiver but also for transmitter. And we saw that there is no theory, there is no some methodology how to create such radars, not only from the picture but from some statistical theory, because we know that measuring like Doppler shift, we have one system. For measuring time delay, we have the other one. For measuring angular position, we have the third one. And all of these systems were created according to some theory. For example, theory of maximum likelihood method, and for some statistical optimization of, for example, according to this one, according to matching filtration of the signals. And we decided to propose of creation of such systems and the theory for creation of such systems. And we saw that it's already existed results for adaptive receiver. It's well known. For adaptive antenna arrays, we found in some international results they have adaptive antenna arrays. For example, Sentinel-1, TerraSAR X satellites, they have already. Also ISI satellite. And this dynamic database, it's also possible to create. And this processor, almost all devices has processor with this adaptive receiver. But adaptive transmitter, there is no theory for creation radars with adaptive transmitter. There is no, and we were searching, and only one that is the most close to creation adaptive transmitter is the theory of nonlinear filtering signals. The theory of nonlinear filtering signals theory of Stratanovich and other scientists in this field. For example, system for phase looking they are based on nonlinear filtration, and we took as the prototype of cognitive radar this system of nonlinear filtration, and this is the classical theory of filtration signals in time, and it's based on minimization standard error criteria. And to solve this problem, it's necessary to solve Stratanovich integral differential equation. And we saw that in these systems we have reference generator that is under control, and this reference generator in nonlinear filtration, it can change its parameters while filtering. So it's a prototype of changing parameter of transmitter in radar, and we decided to use this one. So we proposed heuristic structure of our space remote sensor radar, but the problem is that we obtain signals not only in time, but also we obtain signals in space according to space coordinates from antenna array. So we proposed such systems, and then investigated and decided to state the problem of optimal signal processing. And using such geometry of remote sensing of receiving signal by antenna array, we defined observation equations with noise inside the parameters of the received signals, and we stated the parameters, the model of our main desired parameter of the signal. It's complex scattering coefficient of the surface, or in other way, it's radar image. And solution of optimization problem were obtained from this criteria after solution of Stratanovich integral differential equation. This solution you can find in our paper. And of equation of optimal nonlinear filtration of this parameter radar image, we obtain it. And the most interesting that we had the limit errors of our parameter, and all the next step of measuring the parameter should be performed according to the limit errors. And the equation for limit errors was always also derived. And on the base of these theoretical results, we designed the structure of our cognitive radar that is consist of optimal discriminator 1, optimal discriminator 2, this one discriminator for measuring parameter of the surface, and this one discriminator for measuring limit errors of measurements. And these two channels gives us information about the surface and about the limit errors of this surface. And you can see that here we have connection from our parameter to transmitter and adaptive transmitter in this structure. And finally, we can conclude that we synthesized new algorithm, analyzed its and derived formula for limit errors, and developed a block diagram of the radar for coherent image processing and coherent imaging of the surface. Thank you for your attention. Please ask questions. Yes, Artem Evgenievich, please.
Thank you for your report. It's really, really interesting. And I think that a lot of practical knowledge and mathematical basis was involved to this research. Could you please say what the hardware basis is used to perform all the computations or to process the data? There was a mentioning of FPGA at the diagram with a data flow. So is it the main basis for the processing of all the data in the system? It was the first question.
Okay, yes, really, it is today the most, uh, the highest frequency, not frequency, it's the highest speed, the highest speed of processing. It's of course FPGA, and this structure starts from so difficult technology as adaptive antenna array. That is placed here. Then optimal discriminator, it can be described as a high frequency part of the radar. It's just usual like amplifiers, mixtures, low frequency amplifiers, and other one. Then here should be the analog to digital converter. And here also we have this discriminator with different high frequency parts. And also here must be analog to digital converter. And after this analog to digital conversion, because of high amount of information from antenna array, and maybe sometimes wide band of signals transmitted and received, we have to use FPGA. And all of this other parts like optimal filtration of parameters and limit errors can be realized using FPGA. And
Okay.
these days we try to build such system using this part of 94 gigahertz, and this one part of FPGA. We try to buy Xilinx FPGA up to 3 gigahertz, not 3 gigahertz, 3 giga samples to realize this technology.
If so, there is another question, really important and interesting. Um, you are using really complicated formulas that are really that maybe uh, can be easily executed using MATLAB or another mathematical environment, but it's really not easy to transform the thus computations to the hardware. So the question is, if you are using FPGA as a dedicated platform for such computations, what's the strategy or maybe what's the kind of optimization of such formulas you are using to move all the mathematical basis to this platform?
Okay, this work are based on several years, let us call, experience. We started from the usual one channel transmitter, one channel receiver, the usual theory of synthetic aperture radar. And then we developed adaptive receiver using approach that scattered signal has stochastic structure, and it gave us technology of adaptive receiver. Also, we had some separate works of nonlinear on nonlinear filtering, and also some experience in antenna arrays development. And all this knowledge came to this quite difficult equations and this quite difficult formulas with integrals. So it was a long period for coming this work. And what, according to your questions, I can tell that most of these formulas were obtained with some control of the already existed results. So we saw the other results of other scientists and almost got the same. But for simulation, for high frequency simulation, we use System U technology, and for low frequency simulation, we use MATLAB technology.
Okay. Just to clarify, it's for the moment, thank you. It's clear how the system looks and how the current status was obtained. But the most interesting thing is what the data type, or maybe what the steps you are using to implement all the computations using FPGA. The problem is that you are using some differential formulas and equations, and it can be directly implemented using FPGA because such computations use some float point representation of data, and it's impossible to directly move it to the dedicated hardware like FPGA, and it's necessary to use some fixed point representation and so on. So the question was about such kind of optimization, and maybe is there some methods, maybe strategy to perform such maybe transform of the formulas to move it to the chip. Actually, it was the question, but I think that we hear a lot of details of the system, and actually I received the answer, and we can switch to another question. Thank you for this really interesting report.
Thank you very much. Do we have any other questions?
Alexandros here. Well, thank you for your presentation. I think I can add to the previous question is that I believe part of the calculation can be solved with the IP cores implemented at FPGA. So that's not the biggest problem. I think the biggest problem would be in the long run to get such a complex FPGAs out of USA for industrialization of the product, or moving to ASIC solutions. That would be more troublesome, as I see it. The question for me is that I can see that it's getting quite popular to have so-called digital radars, as people say, trying to implement actually in the antenna array directly, the analog front end. So you kind of push more data and actually have the the first and second stage data transformation done right at the antenna array. Have you worked in that direction?
Not exactly. I didn't have experience with such systems that are called digital antenna array, with exact analog to digital converter from the antenna array. So we did not have such technologies. But the idea when we started this project, it was 3 years ago, and we still try to buy USRP SDR technique from company Ethos. It has 160 megahertz bandwidth, and we can control the operation of this radar using some program, for example, Python or other one. So this is also the idea, to implement such system using software-defined radio.
Thank you.
Thank you for your questions. Any other questions? Okay, then let's move to the second one report.